All right, again, this is Mr. Hayden. This is week 11. This is the chemistry, for people who don't know. Basically, today what we're going to be doing is go over specific heat, kind of talking about an equation. It's not a very hard understanding of like an equation, but it is kind of difficult with learning like when you need to go back and forth with certain things and all that stuff. So what we're going to do is we're going to go through each one. We're going to give you examples, but then I'm going to break off the people from the internet to work on some problems, and then I will actually have the kids in the room, students in the room, working on some as well. All right, so let's go ahead and get going. So again, the essential concept or essential question for this particular part is use, why did it go away? Go away. I don't know why it's still there. What is going on? Okay. Yeah. Give me a second here, guys. Yeah, I have no idea why this is doing this. Okay. All right, here we go. Use one of the examples from this session, and we're going to do some examples and describe in your own words the question and the process of solving the equation. So inside here, we're going to go through a few examples, and I wanted you to pick any of them, and you basically have to kind of discuss how each part gets there, what each one is, and then also discuss what you're actually doing mathematically as you're going through and actually solving for the equation. Okay? It'll make more sense when we get through it, but that's the essential concept, essential question for you guys. People that are coming here, they're actually going to do a little activity. And so at the end, they're actually going to solve some problems. So they don't have to do this. All right. So when we talk about like thermodynamics, thermodynamics is the study of motion of heat. So it's basically the molecules all bouncing around. It's the average of those. And basically talking about how it's transferred from one system to another, from either from one end to another or from its surroundings. So example, this room right now, is it warm or is it cold? Some people said warm. Is it cold? Okay, so some people said warm, some people say cold, whatever it is. It's however it feels to your body, it's your own body. And say you're in a room that is really cold, your body will actually start to get, it'll actually start to cool down. Okay, we have that, you know, your body will start to actually, not give as much heat. It'll actually start absorbing some of that energy, and that's what you have to watch when you're in cold times, because you can actually get get frostbite and whatnot. So what we're going to be talking about is, and usually we use water as an example, but we're going to either actually going to be able to figure out how much energy is actually going to take to move the temperature of something. And you can actually figure out what exactly a material is by that as well. So the transfer of heat could be due to physical change or chemical change. So it could be fire, or it could be a chemical type change, like if you mix certain glycerins with certain like potassiums and stuff, they'll actually create like a fire, stuff like that. And so we're going to go into a little bit of here. This is actually pretty important that you want to make sure you write this down. The equation that you're going to be doing, and we did this equation last week, is Q is equal to MC change of T. That's what that little triangle is, change of T. Q is the heat. It's either going to be in a, you'll see them in joules, kilojoules, you'll see them in calories, you'll see a bunch of various different ways, but the way we're going to do it, it's going to be pretty much in joules, sometimes a kilojoule, but pretty much that's it. 4.184 calories is equal to 1 joule, so you can always make the calculations afterwards. So if you knew how many joules something was, so if it's 2 joules, it would be what? 8.368 would be, that's how many, whoop, I just times it by 2. That's all, times both sides by 2. All right, the M is equal to the mass, that's in grams. It's pretty straightforward. I think that's pretty easy. Specific heat, which is C, is actually done in 2 different ways. It's either done in joules over grams degrees Celsius, or it's over calories over grams degrees Celsius. I think the only way that K-12 does it, if I remember, is just joules. Okay, That's how physics for sure does it, so just make sure you guys pay attention. Now, change in temperature. You guys know how to figure out change in temperature? Let's hope so, right? We did this last week.
Yeah, we learned that last week.
We did? Yeah. So we'll give you an example. Say it's 100 degrees in here. 100 degrees. I go ahead and I turn the air on. Wait an hour. It's 30 degrees now. What was the change?
Yeah, 70.
Exactly 70. Yeah, it would be 70. What we're doing now today is, in theory, you can measure all these other things. I could actually tell you how much energy it took that machine to actually make it drop, the air conditioner outside to make it drop that much. We actually can figure that out. It's actually pretty interesting. So it's the final temperature minus the initial temperature. Okay? Here, let's not worry about that. All right. So here's a practice problem for you, and this is something we're going to be doing in a second, so definitely pay attention to how this actually gets figured out. That's going to annoy me. One second here. Window. Let's see if I can minimize this. Whatever. All right. The best we can. Okay, so how much energy is required to heat 120 grams of water from 2 degrees Celsius to 24 degrees Celsius? Now, this is giving us all the information we need. First, we have our equation. So Q is equal to MC change in T. What's the mass? Help me out here, guys. 120. There it is. Okay, now what is the specific heat? And just so you guys know, as a kind of a trick, water is constant. Just every single element in this world has its own specific heat. Every single one. Water is the one that everything is pretty much kind of compared to. So it is, you can't see it here because of this really cool thing right here, but it's 4.184. I just usually just go 4.18, okay guys? You have to go to 3 parts. Now what's the change in temperature? The final temperature, help me out here guys, pay attention, you're going to be doing this on your own. 24 minus the initial temperature, which is right here. Very good. And just so you know, and this is important, because some of your answers you're going to get will be negative on accident. And you need to make sure that if it goes from a low temperature to a high temperature, it changes in a positive direction. Or if it goes from a high temperature to a low temperature, it went to a negative direction. So see how it went up, went from 2 degrees to 24? It's a positive occurrence. Okay? Make sure you know that because it's going to affect it. Then Q is equal to M times C times change in T. You just multiply them all together. Good for us. Here's a little trick too. Once you know this, you don't need to know what units it's in because look at grams go away with grams, Celsius goes away with Celsius, and the only thing left is joules. So your answer is going to be in joules. Good for us. Here's another one. Again, you're going to do this on your own. So how much heat in kilojoules now is given off when 85 grams of lead cools from 200 degrees Celsius to 10 degrees Celsius? Well, we know the mass, 85. Specific heat is given to you, by the way. All these are given to you. It's on the, like literally it's on the chart with every element and what they are. So you just got to look it up if it doesn't say it. But usually they'll give it to you, and it's right here. So they give it to you right here, which is 0.129, and then you do your change in temperature. You calculate it out, and there you go. Are we good so far? Okay, just making sure. So here's the law of thermodynamics. The first law of thermodynamics is energy and matter can be neither created nor destroyed, only transformed from one energy to another. So example, right now, my voice is making sound waves. Understand that? You're hearing my sound waves, how amazing you guys are. Get to hear my sound waves. Isn't that awesome? Just listening. It's like music. Let's teach music and just talk. No? Whatever. And so it's vibrating the energy is vibrating the molecules in the air and it's transferring to your ear. Energy in this world, because it's not a perfect situation of vacuums and all that stuff, which sound waves can't go in, but you can't, if I just walked outside and I said, hey mom, can you come here real quick? Would she hear me? If I just walked outside and said, mom, by the way, my mom's not outside. Just want to make sure you guys are aware of that. She's like not in the car like waiting for me to get off work or anything creepy. All right, she's in Orange County. So I said, hey mom, can you hear me? Do you think she'd hear me? Why not? I don't get it. Why? But I'm transferring energy into the air. Stupid energy goes away. But it doesn't work. Just like this, you guys in this room can hear me. But if all of a sudden I started playing music, would you be able to hear me? Maybe, maybe not. Or if someone started talking to you next to you, could they hear you? Maybe, maybe not. All these things are interference. And the energy dissipates because of that. It will transfer into others. It never actually goes away. In theory, my sound waves go on forever. But just they change and get manipulated to the point where we actually can't hear it anymore. If you ever go underwater, if you go like this, the light, you can hear it in the whole pool. It's a little different sound type of wave. It's pretty kind of interesting. All right, so the second law of thermodynamics is that any spontaneous process, there will always be an increase in empathy. Sorry, my beard got in the way. Let me fix it. Entropy of the universe. Entropy is increasing. We're not really going to get a lot into that, but that's one of the statements. Third law of thermodynamics is teachers walking fast, creating friction in the room and creating energy. No. The third is entropy of a perfect crystal is zero Kelvin. This is one thing I found was interesting, and it was weird. Like when I was a kid, and I'll just say it real quick, because I was a weird kid taking this class, and I had this thought that to be alive, you have to have molecules, right? And all molecules have to be in motion to be alive. Do you agree or disagree? There have to be movement. Now, at 0 Kelvin, there is no movement. So can matter exist at 0 Kelvin? 0 Kelvin, there's no movement. If there's no movement, I had this weird theory. I even told my college professor, and he tripped out, and he's like, "You should actually write that down and like submit it." I'm like, "Yeah, I'm not going to do that. It's too much work." But I thought that it was in areas in the universe that black holes are areas where 0 Kelvin actually had been created, and therefore there's nothing that gets exists. Oh, that was interesting. I was a really weird high school student who came up with it. As soon as it comes out, I'm gonna, from one of you guys, it'll be like, "Steelers, you stole it. It's on YouTube." You won't become rich. You'll just win like awards and be awesome. It's like, or just laugh at it because it's wrong. Okay, real quick, energy flow. I just brought this up before, but you just got to make sure if it's a negative or positive. We got to see what we're talking about. Was there an increase in temperature? If there was, it was positive. If there was a decrease, it's negative. It's whatever direction you go in. Think of the number line, and if you start at 0 and you go to the left, it's negative. If you start at 0 and you go to the right, it's positive. The same type of idea. It's which way are you going? Okay, exothermic. Exothermic, it gives off energy. Okay, so it will become negative. Endothermic is it absorbs energy or gets warmer. So example, right now, you are, if it's pretty even, your body's not giving or taking, but right now your body is probably exothermic, giving off heat to the air, and the air, on their perspective, your endothermic is receiving the energy. So it's just a perception. Does that make sense or no? By the way, if this at all doesn't make sense at any point, give me a funny looking face. A different funny looking face, Jordan. A funny looking face. No, just give me one of those looks like, oh. There it is. Use that one. Is that hers? Did you borrow hers? Oh. All right. Okay, just so you know, change in heat is pretty straightforward. At a constant pressure, we assume this because we're not going to get into like pressure differences. It's a little much. But we assume pressure is the same. The amount of atmospheres are the same. All right, so let's keep going. You've seen this now. Specific heat is the mass, or I'm sorry, the mass, the specific heat number that's a given, and the change in temperature. This is something, again, you already know, so we will continue. Again, something you already know, 1 calorie is equal to 4.184 joules. Basically, it's water. It's the specific heat of water. Just so you guys need to care. I doubt you care. Ms. Long, you don't care, do you? She strongly cares. Look at her. She cares more than... All right. So do me a favor. Take a look at this equation and kind of work through it in your head and just kind of like walk through it. I'll show you, and then in a second I'll tell you how I do it, okay? Just kind of walk through it. I should walk through it. Is that the funny face? No, different face. Got it. I should be more specific. It was acceptable. It was acceptable, even though you were in my class, a very acceptable face. All right, so for me, when I do this, I write down the equation. Q is equal to ms change in T. You guys all have it written down, write it down, keep that near you on this near the test. And then what I say is, okay, what do I need? What is it giving me? So I just read it. Determine the energy. Boom. Determine Q. So I know they're not going to give me Q. So I just write Q down. Q equals, now I said, well, I need a mass, right? I look at this and go, okay, oh, look at 100 grams. Perfect. 100 grams, write it down. Now if it was kilograms, I need to move it to grams, but I just need to make sure it's in grams. Done. 100 grams, good for me. Then I say, okay, it's water. Cool, I know the specific heat of water. You should have it written down somewhere. It's 4.184 to be exact. Joules over, what is it, grams Celsius. Cool, write that down. Awesome me, yay! Oh wait, I still need one more thing. What do I need? Don't just point at the screen. What do I need? Change in temperature. I need the stuff and the thing and the whatnot.
Yeah, the thing that you subtract.
Yeah, the stuff. All right, so it just said, oh, look, there's two temperatures right there. Good for me. It says it went from 20 to 85. Is that a positive or negative increase? It's a positive then. Very good. So you have a change in temperature of what? 85 minus 20. There it is. And guess what? You just multiply them across. It gives you this many joules. You convert it into kilojoules by just moving it over the decimal place 3 times. 27.2. Good for us. Yay! Yay! Oh, I got excited for no reason. All right, same concept. Hot equal to cold. Now, this equation right here looks a lot longer and more sophisticated and more like one of those. It's really the exact same equation, just equal to each other. What it's saying is, if you were to put it in a situation of if I had water and I had an unknown element, or if I had something I knew like lead, if I know everything about the water, everything, if I know how much energy in the water, I literally could put something else that I know, say the specific heat and the mass, and I can put it in there and I know exactly how to calculate temperature, or I can calculate anything. So we're going to do this once, okay? So look at this. Assuming no heat is lost, what is the mass of cold water at, so one of these is going to have a mass that's needed to be found, which is leaving this one here. For, one second. Okay, gives you the temperature, is needed to cool 100 grams. So I need to make this one my 100 grams, because now it's 2 different types of water I'm talking about. Basically, it's like, well, how much of this cold water do I have to put in this water to change the temperature? So it's 100 grams is needed to cool water from 97.6 to 12. All right? Well, just so you know, if the specific heat is the same on both sides, you can just get rid of it. So they're both water. Now, this is the difficult part, okay? And I just have to make sure I kind of put this to you guys. If I look at this side and I have 100 grams of water, that is 97 degrees, and I go down to 12 degrees. Is that a positive or negative? It's a negative. That's where this comes in. It goes from 12 to that. Now this side, though, is not. It goes from, I need it to be 0. It goes from 12 to 0. See this? So it's a positive 12. That's the hardest part of this whole equation. is understanding which one increased and which one decreased. This is hard because it's water. It's two waters. It's basically you putting an ice cube into water and trying to get to a certain temperature. That's all it is. It's going to get easier when we talk about the other stuff. But you just do the math, calculate it out, and the answer in this case would be, this is how many grams of, let's say, ice that you would need to lower the temperature to that exact temperature. Yay for us. All right, let's keep going. Okay, so I'm going to leave this practice thing on the screen for a little bit, and then what I'm going to do is I'm going to go grab something for the people in class. And they're going to be doing some work on this. So if you need to watch this, go ahead. People on the internet can go ahead and peace out, take off. Let me just check to make sure they didn't do something idiotic. Good there. Good there. I can't remember if I moved anything to Calvin or not. So just want to make sure I didn't do that. Yeah, you can choose one of these for the eccentric question. That'd be perfect. So there you go. I'm going to go. You guys can go ahead and take off and turn in again the answer into the Dropbox to get the full credit. And these guys are going to do other things. All right, I'm going to go ahead and stop the recording. You can peace out when you're done.